So today we're going to be talking about rate of reaction. What exactly is the rate of reaction? So the reaction rate of or rate of reaction, the reaction rate is basically how quickly the reactants change or turn into products. Okay? And the reaction rate um, varies from reaction to reaction because, for example, the reaction between iron and oxygen takes so long, but the reaction needed for the fireworks uh, to appear um, is way faster. So it's really like it's the reaction rate. It differs from a chemical reaction to chemical reaction because some chemical reactions are way slower because of the strong chemical bonds between the substances, which makes the like reaction rate way slower than uh, some other chemical reactions. Now let's talk about the methods that you use to measure reaction rate. These are the two methods for measuring reaction rates. Now, these two methods have have a different formula for finding the reaction rate. For the first method, let us change the color. The the formula for measuring how quickly the amount of reactants decreases is negative change in reactants over change in time, or let's use lower case because capital is for temperature. And for the green one, we just change in products over change in time. We do not use negative outside change in products because we know that to measure the change in the concentration of products or reactants, we should subtract the final amount or the final concentration minus initial. And for reactants, we know that the concentration gradually decreases, okay? Which means that the final is less than the initial, which means that our number or the difference between them will be negative, okay? So we have to put a negative sign outside. So we have to multiply negative by negative in order to have a positive number because we cannot have our reaction rate be negative. Now let us talk about the first method for measuring the reaction rate. Method 1, which is measuring change in mass per unit time. Okay, let us use this reaction as the example that we're going to be using. So in order to be able to measure the change in mass, your experiment setup, the setup for the experiment would look like this. Why do you think the mass will be changing in this case? If you look at the products, you see that there is a gas, CO2 or carbon dioxide. Now, this carbon dioxide, which is being produced, will be escaping from the conical flask. Now, you might be saying, but how is it escaping when there is the cotton wool? The cotton wool does not, so the cotton wool doesn't prevent carbon dioxide from escaping, but prevents acids acid spraying. Now we use the digital balance to be able to measure the mass of the chemical flask and its contents, okay? And we said that the mass decreases because the carbon dioxide that is being produced is gradually escaping, right? So the more product is being produced, the less the mass of the conical flask and its content. And how do we know in this experiment when does the reaction stop? If you look at here the graph, you see that at a point the line becomes perfectly horizontal. Okay, this is at 90 seconds. Okay, the unit here is seconds. You see that the line is straight. By the way, in this graph, the reason why it's descending is because the mass is gradually decreasing, or in other words, because the concentration of reactants is gradually decreasing. Think of it. If you think of it logically, the reactants are making the products, right? The particles of the substances are rearranging in order to produce the products. Now, if these reactants are turning into products, don't you think that the amount of reactants will decrease and the amount of products will increase, which makes sense, okay? So since the concentration of reactants is decreasing, the graph will look something like this. But remember, at the beginning, the reaction is the fastest, okay? Because the concentration of the reactants is at its peak in the at the beginning of the chemical reaction, which is why here at the beginning it is very steep, and then it gradually becomes less and less steep until it becomes horizontal, perfectly horizontal, because the mass stops changing. So here in this experiment, when the mass becomes constant, then reaction ended or stopped. Okay, now let's talk about the second method of measuring a reaction rate. Now we're going to use the exact same example as before. Okay, the exact same example, and our experiment setup will be a bit different this time. It will look like this. So how are you going to be able to measure the change in the products? You're going to use a gas syringe to measure the amount of CO2 in this case that is being produced. So the change, you're going to be finding the change in volume per unit time. Okay? So now, if you look here, we use a stopper. This is called a stopper, by the way, a stopper. We use a stopper instead of a cotton wool. Why do you think that is? So we use the stopper to prevent CO2 from escaping, because then we would be having a change in mass and we don't want that. Okay? Now, in this experiment, how do you think you'll know when the reaction stops? You'll know that it stopped when this plunger, like this thing that is inside the syringe, stops moving. Okay, because as it is being filled up with carbon dioxide, it is taking up the space in the syringe, and this plunger is moving outwards, right? Okay, when the plunger stops moving outwards, in other words, volume becomes constant. Okay, that is constant, if you can read that. Outwards, in other words, volume becomes constant, then reaction ended, okay? Which means that the reaction has stopped. Now, if you look at the graph here, it is ascending instead of descending. Why is that? Like I said before, because the amount of products is always increasing over time in a reaction, while the amount of reactants is decreasing. So this is how the graph for the reactants looked like, if you remember. Looked something like this. It's not really perfect. Okay, this is for the reactants and this is for the product. So this is an important note to have. Now there's a another very important concept to know. Let us say you have A plus 2B equals or yields to 3D. Okay? Let's say you have an equation, a chemical equation that looks something like this. Now, what do you think? How does the rate of disappearance of A compare to the rate of disappearance of B? If I told you that the coefficients represent number of moles. If I told you that the coefficients represents the number of moles, how would you compare the rate of disappearance of A to the rate of disappearance of 2B? The rate of disappearance of A or B is double that of A, because there are 2 moles of B and 1 mole of A. Okay? Now, what about the rate of appearance? So, rate of appearance of 3D, or let's use different color. So, the rate of appearance of 3D. So, the rate, how would you compare the rate of appearance of 3D compared to that of A? The rate of appearance of D is triple the rate of disappearance of A. Why? Because there are 3 moles of D and 1 mole of A. So that was it for this lesson. I'm going to be making a video about rate calculations where we're going to discuss how can we measure the rate of or the reaction rate using the graphs. Okay, so hope you understood what I've discussed in this video. If you have any questions regarding what I covered, you can either comment down below your questions or email me at educology.help@gmail.com. And thank you and hope you have a good day.